Hello dear friends, and welcome once more to another video in our YouTube channel. In this video friends, we shall be looking at how we can test if the series we have here on screen, the two series we have here on screen guys, converge or they diverge. So friends, please stay tuned and watch the video from start to finish guys, because at the end of this video we shall be able to test for any similar series of this nature using the various methods we shall be discussing in this video throughout. So friends, please, for a quick reminder, if you're new to this channel, don't forget to hit that subscribe button looking at you and press the bell icon to get notified each time you upload new videos. And friends, please give the video a like friends, because it took me quite a lot of time to prepare this content for you so well. Thank you very much friends. And friends, please don't fall for all those scammers that use my name and create WhatsApp group and they are saying that they are Humble Mark Academy. Guys, they are not. This is a real Humble Mark Academy guys. All they do is that they demand money from so many students claiming to be me guys. I am not the one, okay? Please, I am not the one. I don't demand anything from anybody. I help my students for free to pass their own exams. Thank you very much guys, and let's get started friends. Excellent guys, so this is what we have guys. So friends, let's start with this series we have here. Let's start with it guys. Great. We have this series from n equal to 2 to infinitive of 1 over n natural log of n. So friends, our goal is to test if the series converge or it diverges. So friends, please, I will give you a small assignment guys. I'll give you a small assignment, so please just put in the comment section down below why the series is starting from 2, not from 1 guys, because I'm sure most of the series that your teachers will always teach you in school, most of them will start from 1, some will start from 0 if necessary. But friends, the series I have here is starting from 2, so just put in the comment section down below why the series starts from 2. I'll highly appreciate that. Great. So friends, we know for sure that we have so many methods in which you can test for convergence of series, right? We have so many methods. So friends, what do you think, which method do you actually think that can work for this series? Because not all methods can work for all series guys, not that. So all you need to do is to try to learn all the various methods, because one method cannot go for all your series for you, okay? So many methods that's different methods are good for different series, good, different of them. So friends, which of the methods do you think we can use to handle this series we have here? So friends, I see the series starting from 2 to infinitive, and this is 1 over n natural log of n. So friends, I first of all see that it is not possible for me to use the limit comparison test. It is trying to prove some resistance, and friends, likewise the ratio test, I cannot do it since I'm going to have 1 over 1. I also see that I cannot use the root test. Yeah, so friends, in this case I'll use the integral test. Great. We use the integral test guys, so we shall be using the integral test. Great. But friends, before we use the integral test, there are some properties that we have to test to see if they hold or not. Great. So friends, in the very first case guys, we are going to be looking at the function that we have here. That's the function f of x equal to x natural log of x guys. This function, that is the sequence itself, okay? The sequence, that is 1 over n natural log of n. We are going to be looking at the function f of x equals to 1 over x natural log of x guys. We are going to be asking ourselves if this function is continuous in this interval, that is the interval from 2 to infinitive and beyond guys. Because to use the integral test, we have to test for 3 things guys. 3 things. 1, it is if the function is continuous in the interval from 2 to infinitive guys. Is it continuous guys? Great. Okay, it is continuous. We can simply just quickly check that. But guys, I'll leave that to you. Okay, I'll leave that to you. You just need to use the various conditions to show if the function is continuous or not. We can start by telling them that the limit as n goes from 2 from above and below guys of this our function guys, it gives us a result that we know, okay, a known result. Great. And likewise, as it goes to infinity guys, everything stays the same, okay? If n goes to infinity guys, we are going to have this our function path turning towards 0, okay? Both from below and above, it turns towards 0. Great. So friends, the limit exists. Great. So this our first condition has been verified. Great. So friends, now we can now start by asking ourselves that is a function positive in the interval from 2 to infinity? Great friends, the function is positive because when you substitute values above 2, all we are going to have are positive values. Great. So this point has been verified. Good. Then friends, the last point we have to verify is that is a function f of x decreasing in the interval from 2 to infinity and beyond? Great friends, it is decreasing. It is a decreasing function since the bottom is heavier than the top when n starts from 2. Okay, the bottom is heavier than the top, so we can conclude that that point has been checked. Good. So friends, once these three criteria have been verified, guys, we are free to use the integral test. Great. So we are going to be looking at, guys, the improper integral going from 2 to infinity of 1 all over x natural log of x dx. So friends, if this integral give us a finite value, that is an answer given from infinity, we conclude that the series from n equal to 2 to infinity, guys, of 1 over n natural log of n converges. Great. But if this our improper integral, guys, diverges or it gives us infinity, that is a non-finite value, guys, we conclude that the series from n equal to 2 to infinity, guys, of 1 over n natural log of n, guys, diverges. Great. So friends, let's go ahead and check that. So in this case, guys, we are going to let our u to be the natural log of x. That therefore implies dx du gives us 1 over x dx. Great. If we make dx the subject, guys, by multiplying all through by x, we are going to have dx to be the same like x du. Great. So now, guys, we are going to be changing from we are going to take the integral from the x world to the u world, guys. We are going to have our table set up of this form. We need the x value and we need the u values, guys. Keep in mind that this 2 and infinity, guys, our x value. Okay, we have at x equal to 2 and at x equal to infinity. Great. So guys, when we need an x value, that is when x is 2 and if x becomes 2, guys, if you put in 2 into natural log of x, right, we are going to have u to be equal to what? Ln 2. Great, as we have it here. Then when x becomes when our x becomes infinity, guys, if you plug in the infinity here, the natural log of infinity is still infinity, guys. We have our u to be infinitive. Good. So in this case, now we are ready to take the integral fully from the x world to the u world. Great. So guys, we're now going to have now the integral going now from the natural log of 2 to infinity of 1 all over x stays the same, guys. Natural log of x is our u. We have it here. Then our dx, guys, is equal to what? X du. Great. So the x and the x, they can cancel. We are now going to having the integral going from ln 2 to infinity of 1 all over u du. Great. As you all know, guys, this integrating 1 over u du, guys, simply gives us the natural log of u. I would have said the absolute value of u, guys, but since our u is the natural log of x and initially the question has given us the natural log of x, so I believe everything is positive because we are dealing with the interval from 2 to infinity and it is always positive in that interval, so no need for absolute values. The limits are going to be, friends, from ln 2 to infinity. Great, as we have here. So friends, plugging in the limits, guys, we are going to have the natural log of infinity minus the natural log of the natural log of 2. Great. And guys, we see that natural log of infinity, guys, is still infinity, still infinity, guys, and the natural log of 2 is a finite value. Infinity minus a finite value, guys, simply gives us infinity. Great. So friends, we can say that infinity is not a finite value, right? So we can conclude that there is a divergent situation. Okay, so this our function diverges. So if we have infinity, which is an infinite value, we can come back here and see that our original series, guys, therefore diverges by the integral test. Great. So friends, we have been able to show that this our series from n equal to 2 to infinity of 1 over n natural log of n diverges by the integral test. Great. So friends, hope you was understood, guys. If there's something you didn't understand, just feel free to leave it in the comment section down below, guys, and I'm going to attend to it as soon as possible. Thank you very much, guys. Then now let's look at the second series we have here, guys. Let's just test if it converge or diverge. So we are going to have it here. So friends, from the look of things, which method do you think can work for this series, guys? Which series convergence test you think we can use to test for the convergence of this series, guys? What do you think? Awesome, guys, awesome. We are going to be using the ratio test. Great. So friends, each time you're being given a series and you see factorial in it, okay, that's a good sign to use the ratio test. Okay, that's a good sign to use the ratio test. It's so good, guys, so cool, because the ratio test is going to reduce it, and it's going to work out so nicely. Great. So friends, this is how the ratio test works, guys. So generally, guys, if we have the series as n goes to 1 to infinity of a n, guys, to use the ratio test, guys, if we can show that the limit as n goes to infinity of an plus 1 over an, guys, as long as this limit gives us as long as it gives us a limit L, guys, once we have the limit L, guys, and case number 1, guys, case number 1, if L is less than 1, the series, guys, converges. Okay, if this our L we get is less than 1, we conclude that the series converges. But guys, if L is greater than 1, we conclude that the series diverges. Okay, but friends, note this important case. Okay, notice so well. If L is equal to 1, guys, the ratio test has nothing to say about the divergence or the convergence of that series. Wait, it has nothing to say about the divergence or the convergence of that series, guys. Take note. If L is less than 1, it converges. Greater than 1, it diverges. If it's equal to 1, the ratio test is inconclusive. It has nothing to say about if the series converge or diverge. We have to use other methods such as the root test, the integral test, the comparison test, and so on and so forth, guys. Okay, great. So friends, let's set up everything. To get our n plus 1, guys, we are going to replace all the n's that we have here with n plus 1 and divide by the original sequence. So we're now going to be taking the limit as n goes to infinity of our sequence was n factorial over n raised to the power ny. So everywhere we put n plus 1, we are going to have n plus 1 factorial other than n plus 1 raised to the power n plus 1. Dividing by the original series simply means multiplying by the reciprocal. That's n to the power n all over n factorial. Great. So friends, please, an important note. Okay, an important note. Under normal circumstance, we are supposed to take the absolute value of this limit. Okay, but I assume that in this case everything is positive. Okay, the ratio test is mostly used to test for positive series. Okay, but if the series is not positive, you may need to take the absolute value sign to take care to make sure that all what you get in the input, guys, must be positive. Okay, great. But since this our series was already positive, I didn't take the absolute value, but under normal circumstances we are supposed to take the absolute value. Great. So friends, by so doing, if we reduce this n plus 1 factorial and the one we have at the bottom, because we have n plus 1 other factorial, we can step down by having just n plus 1 into n factorial. Then all of that, then the one we have done, guys, we can simply apply the law of indices, right? By simply separating these two, guys, we are going to have n plus 1 to the power n into n plus 1. Great. Then we still have our n raised to the power n all over n factorial. We see that n factorial can cancel n factorial at the top, right? Then n plus 1 cancels n plus 1. So in total, we are going to be having the limit as n goes to infinity, guys, of n raised to the power n all over n plus 1 to the power n. Great. So since the numerator has n, has something to the power n, likewise the denominator also has something to the power n, guys, we can simply write it as the limit as n goes to infinity of just what is at the top, that is n over n plus 1, all of that, everything now to the power n. Great. So friends, in this case now, one mistake that students can do, guys, take note, one mistake that most students are going to do is just to put infinitive at this point. They're going to be having 1 raised to the power infinitive and will say that approaches 1. Great. That's bad. Okay, that's bad. Never do that. That's bad, friends. That's the most common mistake that most students will do. They'll just do it, and once the examiner sees it, it gives them, the examiner simply gives them 0. Okay, so that's bad, friends. Don't do that. All we can do, friends, since we see that if, friends, if we didn't have this n here, okay, if we didn't have this n here, we could just simply say that since the degree of the top is the same like that of the bottom, we are going to have the limits be 1. Perfect, guys. Nobody will argue. But since we still have an n outside, and we have n all over n plus 1 inside, guys, it looks similar to the famous series that we all know. Okay, it looks famous. It looks similar to that famous series, guys, but it is not yet in that form. So friends, check this out. If I take the reciprocal of the inside and make the power negative, guys, I'm going to have the limit as n goes to infinity of, now the inside, guys, is the reciprocal. We take the reciprocal by simply having the denominator being the numerator, that is n plus 1 over n, guys. Then what happens to the power? The power simply becomes negative, negative n, guys. So if we split the inside by having n over n plus 1 over n, we are simply going to have, guys, the limit as n goes to infinity of 1 plus 1 over n, all that raised to the power negative n. Cool, guys. Great. This guy looks similar to what we know, right? Great. In this case, guys, our a is simply the coefficient of our a in this case, guys, is simply 1. That is what is at the numerator of n being its denominator, guys, and our b is a coefficient of the power here, guys, and the coefficient is negative 1. So, guys, this simply becomes e raised to the power a b, right? Since our a in this case is 1, that is in red, our b is negative 1, that's the coefficient of the power. We are going to have e raised to the power negative 1. Okay, when n goes to infinity, guys, this is the result we have of this, our form, right? It gives us e raised to the power negative 1, and that becomes what, guys? 1 over e. And we know that e is about 2.7183, right? That is 1 over that, guys, is simply this, guy, simply gives us 1 over e, right? Great. But guys, what is 1 over e? Okay, we have to say something about 1 over e to make the examiner give us a mark. Great. It is less than 1. Okay, it is less than 1. So, guys, we have a convergent situation, right? So this our series has converged. Okay, once we can tell them that this 1 over e is less than 1, it converges. Great. So we can come back up here, guys, and tell them that this our series that is from n to 1 to infinity, guys, of n factorial, all that on n raised to the power n, guys, therefore converges by the ratio test. Great. By the ratio test. So, friends, that is what we have. That is zeta. Please, if there's something you didn't understand, friends, feel free to leave it in the comment section down below, and I'm going to answer it, reply to it, guys, as soon as possible. Thank you so much for watching the video. And friends, please don't fall for those who use my name on WhatsApp that they are humble mark, guys. They are not. Okay, they are not. They are trying to scam students. Don't let that happen, guys. Don't fall for them. This is the real humble mark making the YouTube video, guys. I ask nothing from my students. I don't ask them anything. I just help them to pass their exams. Thank you so much, guys, and see you in the video. Stay safe, guys, and bye bye.